Alright, so today what we're going to be looking at is going to be double integrals over general regions. Now, these double integrals over the general regions are going to completely depend on what type of domain we are looking at or we are observing. But not only what type of domain we're given, but we're also going to be looking at how we want to orient that domain. So one of the first cases that we see is that when we want to orient the domain so that we allow our x variable to change, and we're going to allow our y variable to change with respect to the height that we're going to be observing. Now, if we approach this with the type of integral that we need, naturally the double integral over that region should be the double integral over that function that is restricted to the domain with respect to the area. Now, if we want to simplify it just a little bit more, we can then say that we want to set up the double integral for this function f of x, y, and we want to integrate first with respect to the height that we have chosen, and then we're going to integrate with respect to dx. Now, if you want to think about this, this is as setting your heights to be vertical and then allowing all of those vertical heights to change with respect to the x-axis afterwards. The second type of integral that we look at is what's known as your type 2 integral, and your type 2 integral is going to be an integral that depends on the heights being these horizontal heights. So when we want to look at horizontal heights in the domain that is given, then naturally what's going to occur here, at least in this domain, is going to be that some y values are bounded between c and d, and then we're going to have some functions that are that contain the variable y that are going to make the bounding for these horizontal bounds. So the double integral that we could see if we want to set up this integral for f of x, y with respect to the area over the domain D can be thought of as the double integral where we first generate the heights being the horizontal components for the function, and this is where we have dx first, and then once we fix all of these heights, or once we find all of these horizontal heights, we then want to take the integral with respect to dy, and this is going to allow all the y values to then change. Alright, so over the next examples, what we're going to do is we're going to look at the regions of these integrals, and we're going to identify whether they are type 1 or type 2 regions. Once we're able to identify what type of region we have, then we will be able to set up the integrals and evaluate those integrals over the specified regions.
Alright, so here goes the first example. Now, the first example that we want to look at is this, that we want to evaluate the integral over the specified domain. And that integral is the double integral of e to the power of xy, and that's going to be over some domain with respect to its area. The domain that is given here is all of the ordered pairs xy, such that the y values are bounded between 1 and 2. And that the x values are bounded between y and y cubed. Now in here I've drawn this little diagram here, or this little device that actually helps to say that for the lower bound for y, we're going to take y is equal to 1. For the upper bound for y, we're going to take y is equal to 2. We're going to keep these two equations in our back pocket. Then we're going to say, okay, looking at these restrictions for x, we're going to take the lower bound restriction where x is equal to y and the upper bound restriction where x is equal to y cubed. Identifying that we have these restrictions, we're going to go ahead and we're going to take some time and we're going to make sure that we graph this on whatever specified axes you want. Now, for the purposes of time in this class right now, I've gone ahead and I've drawn out these specific curves on GeoGebra. All right, so one of the first curves that you're going to see here is that we are looking at this curve, and this is x is equal to y cubed, and we're looking at this curve here, which is y is equal to x. Now, using these two curves, we're also bounded by these y values. Y is equal to 1, y is equal to 2. Notice that this then creates some region that we have bounded. And I have this little line segment here to denote how we want to orient or what type of integral we want to evaluate. Do we want to evaluate this region using vertical heights like this? Notice that the vertical height changes as we move through these x values, but then we run into an issue once we get to an x value that is less than 2. That issue is that height, that vertical height, is now dependent on some other function rather than just y is equal to 2. So my thought here is that instead of looking at these vertical heights, what if instead we looked at horizontal heights? Now, allowing the horizontal heights to then change, notice that the horizontal heights never change between these two functions. The left function always stays the same and the right function always stays the same. Their heights, or these horizontal heights, are now dependent on what y value we are choosing, which means chances are we want to set up this double integral with respect to the y values changing first. This will be our dy first. Once we calculate that dy, we can then set up our dx's to change, or vice versa, dx's to change and then dy's to change. So, going back to that problem, I've identified here that we want to set this up using a type 2 integral. Once we've established, hey, we want this type 2 integral, then we want to set our x's to change. Remember, those x values were changing from left to right. The leftmost function was y is equal to x. The rightmost function was x is equal to y cubed. So therefore, x is equal to y, lower limit, x is equal to y cubed, upper limit. Then the y values are allowed to change between 1 and 2. Setting up this double integral, then, we should be able to evaluate this to get us an answer of 1/2 e to the 4th minus 2e. Now, I want you all to do the actual work and go through the evaluation of this integral. And again, you should be able to get this exact answer.